Hey, physics class. So last week we were doing charged particles, like electrons and protons. We had their electric fields mapped out, and we were calculating the forces that they exerted on each other with Coulomb's law. But nothing was actually happening. So all of that falls under what's called electrostatics because there wasn't any action or event. It was just the state of things as they were frozen in a snapshot. We're going to be moving on to some things that actually involve some sort of processes, and the easiest, most accessible way to do that in electricity is with electrical circuits, notably DC or direct current circuits. So we're going to get started with that. Here's our format. I'm going to be up here in the corner. Hello. So you can put a face to the voice. I'm also going to be down here. Hello. Giving you notes, drawing you diagrams, all that good stuff. So let's get started with circuits. So let me just, So starting here with electrical circuits. We explore those with circuit diagrams. So we're going to be, doing this visually with pictures. And that means that we have a vocabulary of symbols that we need to start building. So let me give you your first, term, your first symbol. You know what these are because you live in the 21st century. Batteries are a source of energy that's going to drive this physical system. And the symbol for a battery in a circuit diagram is this. It's two lines, a long line and a short line that are parallel. And the long line represents the positive terminal, the plus side of the battery. And the short line represents the negative terminal or the minus side of the battery. Any battery that you look at should have a plus on one side and a minus on the other side, represented somehow. And there's actually names for these terminals on a battery, which might ring a bell for you if you've been, paying attention to stuff in school, even in other subjects. So, for example, the positive side of the battery is called a cathode. And maybe you've heard of a cathode ray tube or a CRT. That used to be how monitors and televisions worked with a cathode ray tube. They were called, obviously CRTs. But also that was how J.J. Thomson discovered the electron. So we've encountered that before, but maybe you've even heard that from chemistry. Because when you're learning about ions in chemistry, you learn about the positive ions, which are called cations, and then the negative ions, which are called anions. Because this is the positive terminal, that cat, C-A-T, is the root that goes with positive. Speaking of cations and anions, the negative side is called the anode. And you may have heard of that as well. Maybe you've heard of anodized steel. Anodize refers to using electricity to perform a metaling. It's a process that you can do with metal that uses electricity. And when metal has had that done to it, it's called anodized. Anyway, so there are those two words, some context to help you make sense of them and remember them. And if we're going to build a circuit, we need to connect it with something. And the way that you connect stuff in a circuit is with a wire. Again, you know what a wire is. It's just a thin metal strand or filament. And it's just going to be represented with a line. And here's the thing about wires in the circuit diagrams we're going to do. They're highly idealized. And what that means is kind of like how, in the beginning of the year when we were doing force and motion and energy and stuff, we were ignoring friction. We didn't have to deal with air resistance. Gravity was the same strength no matter what altitude we were. All the objects had no shape, no size. They were just a mass. The reason that we do that is because it makes the math so much easier to do. and you don't really lose that much accuracy. So the idealized version of the wire is that it conducts electricity perfectly. There's no loss of energy, there's no waste, no entropy. It's just perfect 100% efficient transmission of energy. Anyway, let's go ahead and make a circuit and use these in the picture. So let me go ahead and just put the battery here. Okay, so we've got our battery. You can see the positive and negative posts there by their line, but it's not connected to anything. So we don't have a circuit yet. Let's go ahead and get our circuit. Let me stick a wire onto the cathode and a wire onto the anode. So that is how you would represent that in the picture. However, it may have wires stuck to it, but we still don't have a circuit because a circuit needs to be closed. This is an open circuit. This would be like the wires in your lights if the switch were in the off position. There's no way to run around this like a racetrack. So we're going to need to continue these lines. Now the actual shape of these wires makes absolutely no difference. What's important is what is connected to what. I could have drawn this as a circle or a long rectangle and it would have referred to the exact same thing. Well, we have a circuit now, and this circuit happens to just connect the positive post to the negative post. In other words, this is kind of like wrapping a battery in foil. It's not a good idea, and here's why. When you have the positive post directly connected to the negative post, we call that a short circuit. A short circuit is one of those terms that's kind of like, in pop culture, that refers to, something breaking or going wrong. But the technical definition of a short circuit is just a power source connected to itself, using up its power on nothing. That is what a short circuit is. And the way that a short circuit makes sense as a malfunction is if it was supposed to run through a whole bunch of stuff, but it could just bypass it and, exhaust the energy with no application at all. Okay, so since we've got a battery and a wire, I mentioned that the battery was a source of energy. And the way that that is done is that a battery contains an electrochemical reaction that's just kind of frozen in place. So let me just sketch that real quick. Inside of a battery, I used blue for battery, so I'll keep going with that. So I'm going to draw like the outline of a AA battery because that's a pretty familiar one. Okay, so we got our AA battery there, and we got the positive post over here, with a little nub on it, and here's the negative post, the one that's more flat. So inside of this battery, there are two chambers. This is a very, very simplified drawing, and they contain two chemicals, obviously, and these two chemicals are often even named on the battery. For example, if you have a battery that is a lithium-ion battery, that's not a brand name. That's from the periodic table. There's literally lithium ions in there. If you have a nickel-cadmium battery, NiCd, they have nickel and cadmium inside. So these two chemicals are separated from each other so that they almost can react with each other. The reaction is halted because this kind of reaction is a redox reaction. And I had to use some lowercase there to make sure that everything came across right. I'm apologizing for not capitalizing everything. If you remember redox reactions from chemistry, you know that this stands for reduction, and oxidation. And if you want to remember how to interpret or how to make sense of redox reactions, maybe remember that Leo the lion says, "Grr." And if you've never heard of that before, then you're welcome. But it means lose electrons, oxidation, gain electrons, reduction. There are certain chemical reactions that involve the gaining and losing of electrons. Well, clearly, if we have a negative side of the battery, that side is going to have excess electrons on it, and the positive side of the battery will have a scarcity of electrons on it. So this reaction can't continue because the electrons can't travel unless you give them a way to go. That's where the battery comes in. If you, oh, there it is. If you connect a cathode to an anode with a wire, all of a sudden electrons are able to travel through that wire and complete the reaction. So when a battery is dead, really all that means is the reaction is complete. And that means that there's no more oxidation or reduction going on that's driving the transmission of electrons. That's the meaning of a dead battery. Okay, well, what the battery contributes, not in chemical terms, but in physical terms, is that urgency for electrons to move. A battery can be dead before the reaction's actually complete, because the reaction has gotten to a point where most of the oxidation has already happened, and there's not an awful lot of urgency for the transmission of additional electrons. And I like to use an expression like urgency to explain how batteries contribute to the circuit, because I think I think that it's an appropriate analogy to kind of get you in the frame of mind to know what's going on in a circuit. But the technical term, of course, is voltage. So let me just write that down. I'm going to put in quotes what this is. Voltage is electrical pressure. Okay, so there is an illustration of electrical pressure that I can do that might also help. In a previous video, I described the electric field around an electron as if it were elevation. And one way that we experience energy gradients, energy differences, is with height. Something that is up higher has more energy than something that is down lower. And we understand what it feels like to put energy into something to move it up. We understand what it feels like to have it dump energy into you when it falls down. So height is a really great way to try to understand how electric energy works. But the thing about gravity is downhill is always down, but this is a circuit, and what's really bizarre is the top of the hill and the bottom of the hill are right next to each other. So that analogy will only get you so far. I want to show you another one that might be more helpful, and it is the water pump analogy. So I've got a syringe here. And the reason that I have a syringe is because you can use a syringe to force the movement of water. So it's going to be my battery because it's going to generate the pressure. You see why I use the word pressure? So I've got a cup of water here. So let me just charge my battery. Just draw some water up into there. There we go. So I've got a charged battery now. In that, I've got water. You know, it's loaded basically. Now, there's just one difference. This water does have somewhere to go. So you'd have to, you know, picture it like with the end stopped up so that if I try to squeeze, it doesn't go anywhere. So that's the idea of a battery not connected to anything. There's pressure on it, but it has nowhere to go, right? So it's like trying to squeeze a closed water bottle. It doesn't actually squirt. So now I need a path for that electricity, for this water to go. So if I were to connect this on here, there we go. So not only do I have a loaded battery, I also have somewhere for it to go. Now, in the in a circuit, I would have to like hook this up to the back of it, and basically the water pressure would push that forward, and as soon as the water pressure was gone, it would be done squeezing and the battery would be dead. However, that's awfully difficult to show, so just I'm gonna, you know, zoom in on one part of the circuit. Here it is. I'm gonna zoom in on one part of the circuit and just evacuate the water like so. Oops, get that in there because I don't want to make a big mess here. All right, so apply pressure. Electricity's moving through the wire. And as soon as I'm done squeezing, the battery's dead. But something's worth noting. See, I don't know if you're able to... Yeah, I think you can kind of see that just from the optics of it. This is actually still full of water. And the reason it's not... Yeah, you can see that, right? It's still full of water. And this is something that is worth pointing out about the technicalities of electricity. And that is that when electricity flows, there are literally electrons moving. However, it's not like electrons have to move through the entirety of the wire because they don't move that fast. They're just passing from one atom to the next. Instead, it works like this. You've got a wire, and in this wire, this is going to be the most unrealistic drawing ever, are a whole bunch of atomic nuclei. Let's just say this is a copper wire. So these are a whole bunch of copper nuclei. These are the nuclei of copper atoms. And all of those atoms are surrounded by electrons. And if you remember your chemistry, or at least your physical science, these electrons are in what's called a sea of electrons because of metallic bonding. Copper has d orbital electrons, and they don't bond with each other quite the same way that s and p electrons do. It's a lot easier to remove them. And so if this is our wire, okay, you can think of this as the tube that I was pushing water through. When you put a battery on it, basically what you've got is pressure, analogously speaking, you have electrons trying to come in this way. The electrons all have an electric field, so the electrons kind of trying to join the wire from this side repel the electrons that are already there. Well, that effect transfers all the way down the wire. And that means that when you put a little bit of voltage here, you end up making these electrons come out. So we are dealing with a wire that's already full of electrons, and as soon as you connect the battery, it's not that the electrons have to travel the entire length of the wire. It's actually that as soon as the voltage is on, they all start moving down it, like it's a conveyor belt. Okay, so we've got the electrons moving in the circuit. Now here's where we really have to be a little upset with Benjamin Franklin. So when Benjamin Franklin was doing doing his early advances in electricity, he, determined that you could have a positive and negative to make the math work out, and he ended up assigning negative to the electrons. Unfortunately, the electrons are the things that move, which means that by that, all of the math would be negative. Well, turns out that doing math with negative numbers is hard, so by convention, we kind of do this a little backwards. So let me draw my circuit again. I've got the battery, and I've got a wire. The physical reality is that electrons are traveling from the anode to the cathode. This is what's really happening. However, the math is hard. So, what do we do when the math gets hard? We either quit or we change the math. So, here's the redesign. What we do is, I'm like embarrassed for physics to have to even tell you this. What we do is we just imagine that positive charges are moving in the opposite direction. I mean, it's a fiction, but kind of a lot of this stuff is semi-fictional, so we're going to go with it. We're going to have that be the mathematical representation of this actual current. Instead of negative charges moving counterclockwise, we're going to have these imaginary positive charges move clockwise. So, I guess I can call this fake but easy. I mean, we're not going to be turning down easy now, are we? All right, we don't need more negative numbers in our lives. So, when we're drawing diagrams and we're drawing arrows and stuff, look, if we're just trying to solve problems and get answers to, graduate or something, that's fine. But if you want to understand what you're doing, which I trust you do, and you want to actually learn some reality about the universe, then I want you to get that what's really happening is negative charges moving from an anode to a cathode. However, by convention, we have imaginary positive charges move from the cathode to the anode. Okay. Well, there is more to circuits than this. So, let's move on. We have to put another element into our circuits now. And let me go ahead and demonstrate that physically. So here's our water again. I'm going to draw some water up. I'm going to charge my battery. Okay. So I could just squeeze the water out again. But like, why? It seems like a waste of energy. Can you think of some things that have been powered by the moving of water? I mean, that shouldn't be too hard to think of. That is one of the earliest renewable sources of energy. You know, like a mill on a river or on a stream even. Hydroelectric power on a river. You can use moving water to power things. Turns out you can use moving electrons to power things too. So if I were to put this into some sort of a apparatus, you know, where the movement of water was actually causing some action I wanted it to cause, well then that phenomenon, whatever I'm making happen, is going to use up some of the energy that I'm going to be putting into squeezing this. In fact, it's going to make it harder to squeeze this because I'm not just moving water, I'm now also doing that thing that this is accomplishing. So I'm going to model that like this. So I've got this paper towel here, just in case of spills with this water. So what I'm going to do is just going to take a little piece, going to make it nice and narrow. I'm going to stick it in there. Now that's not a very effective way to stop that water, now is it? I mean, if I had stuck in like a piece of plastic, I'd be blocking the stream entirely. But because it's a paper towel, it can actually let the water through. So I'm going to go ahead and just see how that works. So I have to gently apply pressure, otherwise I'll just shoot it out entirely. But if I squeeze this, I should be able to get some to actually come out. Yeah, see, there you go. Well, it's a good thing I record these, otherwise I just ruined my notes. Okay, so let's close that. All right, so there are some things about this that should be obvious. That it's harder to get through a paper towel with tiny holes than it is to get through just an open tube, which is just one large hole. In other words, there was an energy expense just to move through and get out. So in the context of a circuit, that paper towel was resisting the flow of water. And so we have our last term and our last symbol a resistor. Now, a resistor is going to be symbolized with a zigzag. And a resistor is just something that costs energy for electricity to pass through. And it's often used to accomplish a task because you can think of it as a way for energy to leak out of the wire. One way that you might use a resistor is as a heater, as in when electricity tries to pass through the resistor, some of the energy escapes it and it just enters the air as kinetic energy. Well, kinetic energy of air, if it's not wind, is heat. This could also be used, say, to produce electromagnetic radiation in the visible range, so like a light bulb. You can do lots of things with resistors, but rather than specific application, we're just going to deal with what they contribute to a circuit. So I'm going to finally draw one more circuit. Make sure you've got variables and symbols, and then we can actually do a calculation with an equation. Hooray! So let's go ahead and get that battery again. And remembering that it's supposed to have a voltage, let's actually make it be a battery. So just so we can have a familiar battery, since I did a AA before, let me go ahead and make this battery have the same voltage as a AA. That is 1.5 volts. So this is a 1.5 volt battery. Okay, that just means that the reaction inside of that battery is sufficient to produce some urgency for the electrons to get from the anode to the cathode. And the way that you would compare that urgency to some other battery is on a scale of volts, and this one registers a 1.5. Okay, green marker for the wire. So we're going to go ahead and stick a wire on. This is still an open circuit. We don't have any electricity flowing yet. But now we will, because I'm going to close the circuit, but I'm not going to have a short circuit. This time we're going to stick a resistor in there. Now, different resistors can resist electrical flow to different degrees. And the unit for resistance is called an ohm. So actually I should write that up here. OHM, and the abbreviation for that is the Greek capital omega. That's the last letter in the Greek alphabet. It's an O. Okay, so ohm. Let's see. If we want some sort of resistance on here to make some sense, I'm going to go ahead and make this be a low value, 3 ohms. Just to give you an idea of how low that is, real wires have a resistance of 3 ohms. So I'm only doing this for mathematical simplicity. Now that I have an actual circuit, I can now sketch out the electricity and which way it's flowing. Now remember, the actual flow of electricity are electrons moving from the anode to the cathode, but we want our math to not be full of negative numbers, so I'm going to have to draw an arrow pointing the wrong way, right? And it's going to be like that. Now I've got a voltage, I've got a resistance, and now that it's actually connected, there's electricity flowing. This is the last thing that we need to add to our list of vocabulary. It's current. And that's the flow of electricity. It's measured in a unit called amperes, which is abbreviated as amps. And the symbol for current is I. Okay? So the 3 terms we've got are voltage, current, and then resistance. Its unit is amps, but its symbol is R. Now, those 3 terms actually relate to each other like this. This is called Ohm's law. And using this, we can actually determine how much electricity is flowing in this equation. All right, well, let's go ahead and do that. The voltage is 1.5. I'm going to use the colors to keep it straight. The resistance is 3. This equation shouldn't be too impossible to solve, right? It should be 0.5. 0.5 amps. So 0.5 amps, if you convert that, would be 500 milliamps. And if you were to find, say, like your cell phone charger, you might actually see that it has a power rating on it, might even be 500 milliamps. Anyway, that's a perfectly reasonable circuit, except that no one would use a resistor as small as 3 ohms because, like I said, that's basically a wire. Anyway, that is a basic setup and overview of circuits, terminology, and symbols. And we will do some more interesting stuff with that next time.